So let me open up a sketchbook and we'll review briefly what is LU decomposition about. Do I have any? Oh, I don't have any. Just a second. Oh, okay. I have plenty here. All right. So let's say that I have a situation, okay, situation number one, where I am working on a problem, and actually that situation where we had a heated rod, okay, was a great example of that. So let's say that I want to set that system up, and let's say that it's a large system, so I actually end up discretizing my rod to like 1,000 or even 2,000 points, and every time I will have then, say, 2,000 by a 2,000 system to solve. And I'm constantly solving the same differential equation. So my heat transfer coefficient with the environment is the same. Okay? The length of the rod is the same. Things are the same. The only difference that I'm making is in changing that boundary condition temperature. Okay? Now I'm not sure if you remember, but actually the only thing that you end up changing is that right-hand side. In solving for Ax is equal to B, only thing that you're changing when you're changing boundary condition in terms of temperature is that you're changing that right-hand side. All of the others, if I'm leaving the parameters, the physical parameters the same type of the rod, the same type of the heat transfer between the rod and the air, remain the same. Okay. So let's say that I'm doing the whole benefit of modeling is that you can go, if you have a good model, you can set up the simulation and run it 1,000 times and see what the outcomes are. So once you see all of the outcomes, you know how to plan your operations. That's what's happening in reservoir simulations. That's what's happening in any type of engineering problem. So the whole point is that it's kind of cheap. You press the button 1,000 times and you actually get the results back. And that helps you plan. Okay. Now, if you're doing that 1,000 times and the only thing that is changing is your right-hand side, then you'd like to speed yourself up. Somebody here pointed out that basically LU decomposition speeds things up. And let me just make a point out of that. So situation number one, so I'm going to say why LU decomposition. Okay. So basically, I am solving Ax is equal to, and I'm going to say B1, Ax is equal to B2, Ax is equal to Bn or M, however you want it to. So I'm solving multiple systems with the same A, okay? And the only thing changing is right-hand side B. Okay? So I'm wondering if I could essentially solve some part of this problem just once and then just work on the remainder, and that will speed me up. And that's what basically LU decomposition is. Now, why is that important? It's important because Gaussian elimination in itself, okay, there's that forward elimination step, okay, that basically transforms my matrix into upper triangular system, okay, and then there's a backward elimination, so there's the two steps, right? And the first part is the one that I can actually kind of do once and record, and the second part is something that I can essentially do twice. Do only as my B is changing. And the problem is that there was that notation probably wasn't clear. So in the slides, they said something like, okay, this whole process of Gaussian elimination is something called O of NQ. This notation O of NQ comes from the following. It's order of NQ. We don't know whether it's 2NQ or NQ plus N squared or something of that sort, but it's on the order of NQ, which is basically what scales your time. And it comes from this. You say actually that you are doing N operations essentially in a for loop for I is equal to 1 to N. Let's say that I'm saying C of I is A of I times B of I. This is just some vectors A, B, and I'm computing vector C. If I do this in a for loop, okay, how many multiplications will I do? N. Okay, so this is basically N multiplications. And maybe I'm doing something else. Let's say plus D of I. Okay. So in this process, we're going to say, okay, I'm doing N multiplications and N additions. Okay? This is what I call O of N. And maybe there is one more. Okay? I'm going to call all of these operations like this O of N, because they scale with N. On the important scale, in terms of time, it really is dominated by this size of the vector N. Okay? And it scales with the size, linearly with that size N. Okay? So this is basically where I have N multiplications and N additions. So overall 2 N operations. Okay? And that's what's expensive on your computer. I mean, it's not necessarily very expensive. Okay? We need computers very fast. But there is a limit. Okay? How many so-called floating point operations per second you can do? Okay? So people who analyze algorithms, they basically literally go and you look at the algorithm like this and you count how many operations you do. Turns out, okay, so this is so-called O of N operations. Again, whether it's 2N, 3N, 2N plus 4, it's kind of all the same in the great scale of events. Okay. The big difference, which really has an order of magnitude impact, is when something is N squared versus N. Okay? And again, 2N squared versus 2N is irrelevant. What's relevant is that if I increase my problems 10 times, okay, if I have O of N operations, my workload will increase 10 times. But if I have O of N squared operations, my workload increases 100 times. Okay? So soon enough, I'm running out of the memory of my computer. Okay. So in essence, so O of N squared, O of N cubed, this is deemed very expensive. Okay? Increasing size of the problem. No, not sure what's going on. Oh, hi. Started mirroring my size of the problem. Increases work. So size of the problem 10 times increases work 100 times. Okay? So 10 squared. And if I have O, yes?
So is it for N or is it for the exponential?
N is just the size of my vector, or size of my problem in terms of vector or operation. So in solving AX is equal to B, n would be n by n is the size of the matrix A. Okay, so one linear size of matrix A.
What does that say after increasing?
Increasing size of the problem 10 times increases work 100 times. 100x, 10x. Okay? And if I have n cubed, then increasing my matrix from 10 by 10 to 100 by 100 increases my workload 1,000 times if the problem is O of n cubed. And this n cubed simply comes from how many operations do I do for all of the steps. Okay? So Gaussian elimination is in itself O of n cubed, and we didn't go into counting everything up. Okay? And that's a lot. Okay? Good algorithms are O of n. Those are being fast. And computer science deals with analyzing algorithms literally by counting up operations a lot. Yes. And O of n squared is already bad. N log n is typically a good compromise. Okay? So anything is done to actually reduce that, yes.
I'm just wondering, that example that you wrote, is that like an O of n or n squared?
This is O, just this for loop is O of n.
Okay.
But if I have double for loop, it's going to be n squared. Okay? So I'm going to get n squared if I have a nested for loop. 3 nested ones, and that's already getting to n cubed. Yes?
She's saying if you change this with it in natural logarithm, increases your times.
Yeah, so basically I would get here n squared if I had nested for loop.
So then you can not have a nested like you said with natural logarithm.
Well, you have to be smarter about your algorithm. So our Gaussian elimination wasn't smart. Okay. It had a nested for loop.
Was it in Q? Is it?
Total is n cubed. Okay, so essentially this is the problem. So nested for loop will do that. Okay, so this is just to understand. Again, we will not do a lot of exercises counting. This is just for you to understand how algorithms are actually analyzed. Okay? This is an introductory class, so this is probably a little... Okay, so essentially Gaussian elimination is O of n cubed. And if I do Lu decomposition and I have to really speed things up, then I'm doing this expensive step only once, and all of the following ones are O of n squared. Okay. And Lu decomposition helps by doing the most expensive part only once. Whoops, once. So this is our motivation. Second problem, so this is just solving multiple systems. In one special case, where I actually need to solve for multiple systems like this is, what is the special case? Where I'm gonna get a number of systems like this.
Question. So you were saying the nested for loop will do n cubed?
Nested for loop will in itself, if it's something like this, is gonna do n squared. But Gaussian elimination has so much within that's gonna end up being n cubed.
Oh.
Okay. Because you will do nested for loop, and then within each line you're also gonna have all of those partial sums, if you remember, and they're order of n. Yummy. Okay, those yummy sums that you had. So that's what ends up being n cubed here. In essence, even if you have the simple loop, if you have n operations here, that's going to be n squared. Okay. So finding an inverse was actually one case like this. How so? So basically, what is an inverse of a matrix?
It's just the augmented matrix with the actual matrix.
It's
Operations on there.
So it becomes inverse. Okay, but what is an inverse of a matrix? You describe how to find inverse.
the
What does inverse mean?
Inverse matrix is matrix, okay, it's like A to negative one, the inverse of A.
Inverse. So essentially, if I had number 2, I multiply 2 by 1/2 and I'm going to get 1. So 1/2 is inverse of number 2. Now I'm defining the same thing but for a matrix. Okay? So essentially, A inverse is the same as A inverse A, and it's identity matrix. So I don't have 1 now, but basically a diagonal matrix with all of the ones on the side. So let's say, I don't know, let's do a very simple matrix. So let's say that I'm looking for A inverse is equal to identity. So there's this A, and this is A inverse, okay? And A inverse, let's say that this is a 3 by 3. Okay? Then A inverse is the same size. Okay? And essentially I can think about it as x, x2, x3, where these are columns. Okay. So A is something I know. These are my column vectors, x1, x2, x3. And when I multiply that, it has to be 1, 0, 0, 0, 1, 0, 0, 0, 1. Now when I'm, yes,
So those be the column vectors of the inverse?
of inverse, yes. When I actually multiply this, the way multiplication, matrix multiplication works, this is, and you can convince yourself by doing it by hand, is this is actually A applied, so basically A times the first column, A times the second column, so it's basically a matrix with 3 columns, and each column is A multiplying this column here. And that has to be equal this identity matrix. So looking for inverse of matrix A is equivalent to solving which 3 systems?
Okay, x1 equal to 1, 0.
That's my first system. Second system is AX2 is equal to 0, 1, 0. And the third one is AX3 is equal to 0, 0, 1. Does everybody see that?
Yeah.
So basically I'm solving 3 systems with the same A, and the only thing that is changing is what I put on the right hand side. So this is right for LU decomposition. Okay? So this is 3 systems with the same A, and my right hand side, which I'm writing as RHS, is 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay? So these are my B's that are changing. So you can call this B1, B2, and B3. Yes?
If I ask about the previous condition number,
We're gonna get to that.
Oh, you're gonna take, okay.
Did you go in slides through those?
No.
No. So we're gonna go through that today.
Oh,
I'm just reviewing the point. I'm not sure if the point was, if you got the point last time, why are we doing Elimination decomposition? So I'm just reviewing the motivation. Now find, this is basically then the procedure. So, okay, if I actually have, if I have a problem that I'm trying to use the LU decomposition on, okay, we first do what? So let's say that I have a set of problems that I'm trying to solve. So what are the major steps? Step one is to get this L and U matrices, and A is equal to LU this is lower triangular, and it also has, in our, the way we're solving, it has ones on diagonal, and this is upper triangular matrix. And this is a step that is very similar to what we actually did in forward elimination for Gaussian elimination. So that forward step, you essentially try to get A to upper triangular matrix, and on the way you're just carefully recording elements of L. And then once you have L and D, okay, L and U, then first you will actually find D such that it solves LD is equal to B. So this is now, L is lower triangular matrix. So this is so-called forward elimination. You will immediately see what your first D1 is, and then you just plug it into the ones below and you find everybody else. And then you find X such that UX is equal to D. And X is your solution. As your B changes, so this you do typically when you have AX is equal to B with multiple right-hand sides B, you're going to repeat, this is the only step you're going to repeat if you're doing this multiple times. So this step one you do only once. Only once. And this repeat for every right-hand side B. Okay? Yes?
In terms of finding your L matrix, if you want to do a row times coefficient plus, like the third row, you need to change the signs of each of your coefficients.
Right, so it's, in that case, so just stick to the choices. Yeah. Alright, so this is just a quick review.
Did you say from second hand side or at each?
For every right hand side B. So this is the part that you're going to repeat. And this one you've done only once, so you saved yourself the one.
So how many steps you need to repeat depends on n, right?
Yeah, so here I would repeat this 3 times. Okay. This step only once, and then for each B, I would get an X, and then I would put them together as columns and get what my A inverse is.
So this operation is like O3, 2, because the n is.
So this is O of n cubed, but this is O of n squared, and you do this 3 times as opposed to 3 times O of n cubed. So you do O of n cubed once as opposed to 3 times. That's the time saver here. This is the expensive part, okay? And that you do only once.
That's the Q.
So just think about it as the expensive step. I was just explaining what n cube means, okay? But just focus on this being the expensive step that you do only once instead of 3 times in this particular case. But if this was n by n, you will do this n times whatever n is. Okay? This is 3 by 3 system, so you do it only 3 times. Yes?
Is there faster method than decomposition? No.
Finding inverses is expensive business.
Could you explain how exactly we form L with the coefficients?
Okay, so let's go through one of the steps. So I'll just repeat. I don't know if that's probably what you did last time, but I'm gonna repeat that because right now I don't have any other prepared. Okay. So this is just a quick repeat. Okay. So let's say that your A example from last time. So your A is -3, 2, -1, 6, -6, 7, 3, -4, 4. And whatever the B was, let's just do the Lu decomposition part. Okay. So what I'm looking for, okay, technically I'm looking for L that is lower triangular and that has 1, 1, 1 on the diagonal, okay? And it has some L2, 1, L3, 1, L3, 2 that I don't know. Okay? And my U is U1, 1, U1, 2, U1, 3, 0, U2, 2, U2, 3, U3, 3, and the rest are zeros. So this is the lower triangular, upper triangle. So basically I start with my A. Okay. And now I kind of stick to the same choices just to be consistent, otherwise I might mess up these coefficients. So I'm going to replace my second row, replaced by 2 minus A21 divided by A11 times 1. Okay. And basically this here is going to be my L21. Okay. So my L21 is then A21 divided by A11. And in this case, it's 6 divided by -3, so it's -2. And this is basically 2 minus -2, it's +2. Okay? So when we do that, I'm going to have -2, 3, -1. So this is going to be 0. Okay? Minus 2 times 2 minus 6 is -2. 2 times -1 plus 7 is 5. And I need to now do second replacement. I'm going to replace this 3 minus, okay, A31 over A111. So this means that my L31 is A31 divided by A11. And that, in this particular case, is 3 divided by minus 3, which is minus 1. And this simply is, so I basically just sum up 3 and 1. So when I do that, minus 3 plus 3 is 0, 2 minus 4 is minus 2, minus 1 and 4 is 3. And my last one left is replacing this one. Okay. And we're going to replace it by 3 minus A32 divided by A22. This is what in actual slides, I actually refer to these as tilde because these are some new coefficients A. They're not my original A. So I can't just go to my original A and grab A32 and A22, okay? I have to get here. So then my L32 is actually this. And that is minus 2 over minus 2, which is 1. And when I do this transformation, I'm going to squeeze it here. Minus 3 to minus 1. 0 minus 2, 5. And this last one is 0. Minus, so minus 2 minus minus is 0. 3 minus 5 is minus 2. Okay. What is my U?
Your upper thing, that is.
This one here. So this is U. Okay. What is my L? So my L is, I have 1, 1, 1. Minus 2, minus 1, 1. And this is my U. Who has MATLAB open? Can you multiply L and U, please?
L is the dot. Multiply L and U.
Yes.
Oh yeah, I just wanted to get one more clarification. So when you're replacing the rows, what exactly is the rule that you're following with doing that?
This one. So this is what we did in class when we were programming as well. Okay? So when I'm replacing, I'm replacing, here technically I have a choice of doing minus 2 plus A21 over A11. Same thing in terms of just making that coefficient 0 there. Okay? But stick to this choice so that you have a consistent.
Okay, because that's what I found during the homework, that if you did something else, like if you did a different...
Yeah, you kind of get like, because that's changing. And I didn't go into proving that this works, because that would take us. Right? But essentially, just if you multiply it here, so if you multiply your actual U11 is the same as A11. You can see that when you multiply things. Okay? And then you see that L21 times U11, which is A11, plus 0 has to be equal to the first one over there. So you can actually go get that little by little, okay? Because your A21 has to be equal to L21 times U11. Okay?
We just follow the 2 minus 1.
Yeah, so L21 is actually very easy to see directly here, but just by multiplying these two matrices and see what's there in A. But then not everything necessarily is, because you do these transformations.
Okay, then for those transformations, just follow some
Right.
of what you did right here.
Right.
Minus one.
Just be constant. Okay.
Yeah.
Got it? You got it right? All right. Yes. Very good. -2. Again, A31 divided by A11. My A31 is what? Oh no. No, this is -2. L21. A21 is 6. 6 divided by -3. These are positions in A. This one? Hey, shh. So this is my ultimate product of this procedure is U.
Yeah, no,
It's upper triangle.
I don't understand how you use
If I replace 3 minus 2. So this is my third row minus second row. 3 minus 5 is -2. Okay? And -2 minus -2 is 0. So this is a 0. Okay? So this means third row minus second row. Okay? Other questions? LU decomposition is your guaranteed question on Monday.
Oh.
Oh, yeah. There's that test business we're doing on Monday, right? We're doing that. Alright.
Will it be by hand or do you also have
By hand.
and then we'll probably have to write out like the loop for the code.
No, for this I'll probably just ask you by hand.
So shouldn't I share it down?
Well, you already did Gaussian elimination. It's not more complicated than that. Okay? Yeah. Remember that you had to come up with the coefficient? Store it. Right? You get your L on the as a result.
So this is,
Huh?
so the process of getting the upper triangle, is called a naive Gaussian elimination.
Yes.
So it's naive.
Well, yes, and the one without changing pivots.
Without making the pivot.
Without pivoting. So non-naive one will always try to minimize the numerical error. So it will always try to get the largest number of positions up there and change the rows accordingly. All right. I have to always do replacement of the entire row. And this is like Gaussian elimination. I'm just recording things as I'm going. Because that's what I have to do. Those are the coefficients. And I'm calling them tilde because these are already changed coefficients of A. They're not the originals, right?
Wait, so naive is when you don't swap the rows?
Hmm?
Naive is when you don't swap rows?
Yeah, so we didn't swap anything here. But normally, and this is why if you're using LU decomposition on MATLAB, it might actually switch rows and columns. So the result might be confusing. So just be aware of that. Okay. So let's now just continue with some basically more definitions and looking into or touching upon the problems one might come in. So again, here I just did an example of LU decomposition. Okay? If you were actually solving the problem using LU decomposition, then you would go through 2 more steps. First, you would solve for D such that LD is equal to B now that you have L. Okay? And that's simple. So your D1 kind of is staring you at you right there. then you just plug it into and get a D2, plug D1 and D2, get D3. So that's straightforward, and these are simple to solve, okay? And then one more step is solving Ux is equal to D. Since U is upper triangular, this is backward substitution. It's as simple to solve as this previous one. So these two steps gets you to actual answer you're looking for. And you repeat it as many times as you have this right hand side. Okay? All right. So next thing that we're going to introduce is matrix norm. And matrix norm is a measure of a matrix, just like absolute value is a measure of a scalar. And we introduced all kinds of norms for vectors. And the point that I made there is that we engineers, we like comparing things, right? So I need a norm to compare things in, especially if I have a set of n numbers. Now, the way matrices come about, we care how easy or how hard it is to solve a matrix, or basically a linear system AX is equal to B. Because again, more than you realize, in every computational method out there, ultimately you're going to come down to solving, even though you're actually thinking you're solving a differential equation, it comes down to a linear system. Okay? So in your reservoir simulation, you will actually see an entire hordes of people working on optimizing how to solve AX is equal to B for the particular problem in the reservoir engineering. And basically, those are called preconditioners, and you will hear about people working on preconditioning matrix A so that the problem is easier to solve. So that's basically, there's an entire line of work of speeding things up. But before that, let's actually evaluate how hard or how problematic it is to solve AX is equal to B. So we introduced norms for vectors, and now we will actually introduce norms for matrices as well. So first and simplest one to compute is so-called Frobenius norm. Okay? And that one simply takes sum of the squares of all possible elements of the matrix and then takes the square root. So this one is straightforward to actually find. So if I asked you to program finding this Frobenius norm, would that be complicated? If A is only A is input, some little nested loop, sum over all of elements, we know how to do that. Great. Could be, I don't know, depends. This is actually more exam 1 actually. Second one, and that one's not so obvious, okay? So I'm probably not going to ask you to compute this one. Let me just finish the sentence. Is 2 norm, okay? 2 norm looks at how does A map a vector of size 1, or length 1, and looks at all of those vectors and finds a maximum. So there is A mapping my vectors of length 1 for those that are known to, and that's going to be norm of the matrix. So much harder to find. Okay? This one I will not ask you to program, but MATLAB will return it for you. All right. You there? Wait, how was last night?